Hey there! In this video, we're going to look at how we can find the absolute value of a complex number, which is a number that is composed of two parts, a real part and an imaginary part. So first, let's just review what we know about finding the absolute value of a real number. It's pretty simple to calculate. The absolute value of a positive number is just that number itself, and the absolute value of a negative number is the positive value of that number, and the absolute value of 0 is just 0. Well, where does that calculation actually come from? The interpretation of absolute value is that it measures the distance from 0 on the number line. We've seen that we can represent the real numbers as a one-dimensional line with the positive numbers on one side and the negatives on the other. So the reason that the absolute value of -4 is 4 is because that distance from 0 is just 4 units. And this interpretation also allows us to find the absolute value of an imaginary number. So we've seen that just like there's a number line that represents the real numbers, the imaginary numbers can also be represented as a number line. It's just a number line that exists in a different dimension. So to find the absolute value of 3i, we're going to measure the distance that 3i is from 0. Well, just like we have on the real number line, this is broken up by units, so the distance that 3i is from 0 is still just 3. So the absolute value of an imaginary number is just the positive component of that imaginary number without the I. And the absolute value of a negative imaginary number is still going to be the distance from 0. So if we want to measure the absolute value of -2i, well, that is 2 units away from 0 on our imaginary axis. So the absolute value of -2i is +2. So that's pretty straightforward as well. Where this calculation gets more interesting is if we're trying to find the absolute value of a complex number, because a complex number exists in 2 dimensions. Recall that we have the complex plane here, which is what we get when we put together the number line of real numbers and the number line of imaginary numbers. So if we want to measure the absolute value of this complex number, 3 plus 4i, which I've plotted right here on our complex plane, well, that means that we're trying to measure this diagonal distance right here. So how do we find the distance of a diagonal like that in 2 dimensions? Well, it's pretty cool. We can actually use one of the techniques that you've learned about in geometry. So let's zoom in a little bit on this diagonal. What we can do is first measure the distance on our real axis of this component of that complex number. So the real distance on our real axis is 3 units. And if we measure this vertical line here, that would give us an imaginary distance of 4 units. So in order to measure this diagonal distance and find the absolute value of our complex number, what we're really trying to do is find the diagonal in a right triangle. We're trying to find the hypotenuse. So if we call this side of our right triangle here 3, and we call this side of our right triangle 4, you probably remember the Pythagorean theorem, which is a relationship between the sides of a right triangle. What it says is a squared plus b squared is equal to c squared. And the absolute value that we're trying to find is this distance c, the hypotenuse. So we can plug in our real distance is 3 and our imaginary distance is 4. And that will equal the square of this diagonal distance. 3 squared is 9 and 4 squared is 16. So that tells us that c squared is equal to 9 plus 16, which is 25. But that's not our final answer yet, because 25 is not the diagonal distance, it's the square of the diagonal distance. So if we want to find just that distance on its own when it's not squared, we can take the square root of 25, which is 5. So that tells us that this diagonal distance is equal to 5. And that is the absolute value of that complex number. So let's look at what we did to work through that. We found the real distance and the imaginary distance separately. We squared each of those two values and added them together. And finally, we took the square root of that value to get our complex distance. So here's a summary, once again, of the formula that we can use to calculate absolute value. But I don't just want you to know that formula. It's important that we see why this really makes sense is because we're calculating a distance in 2 dimensions. So let's work through another example on this page, and then I'll put up some more examples on the next screen if you'd like to see those together as well. To find the absolute value of 3 plus 3i, we're going to take the square root of, well, our real value is 3, and then we square that. And our imaginary value is also 3, and we'll square that and add those together. So this is the absolute value of 9 plus 9, which is the absolute value of 18. The answer to the absolute value of a complex number will always be a positive square root of some number, which makes sense because when we're measuring distances, we're just talking about positive quantities. And remember that when we're dealing with square roots, we can simplify a square root by factoring it into perfect square factors if possible. So because 18 can be broken down into the square root of 9, which is a perfect square, times the square root of 2, we're going to simplify that square root of 9, and we would get positive 3 times the square root of 2. Alrighty, so let's look at a lot more practice. And if you'd like, you're welcome to pause the video here, try to work through these on your own, and then you can check your answers together. Or if you still want to work through it together, let's do that right now. So the absolute value of 4 minus 3i is the square root of 4 squared plus negative 3 squared. And when we're calculating absolute value, it's not really going to matter if our real or imaginary components are positive or negative, because of course a negative times itself still gives us a positive answer. So this would give us the square root of 16 plus 9. Negative 3 squared still gives us positive 9. And that's the square root of 25. And now here's the point where if we can, we want to simplify our final answer, either by taking the square root of a perfect square or seeing if we can factor out any perfect square factors. Well, 25 is a perfect square. Its square root is 5. When we find the absolute value of 4 plus I, if we just see I on its own, we can think of that like it's the imaginary part, 1I. So we're going to do the absolute value, or I'm sorry, the square root of 4 squared plus 1 squared. That's the square root of 16 plus 1, which is the square root of 17. 17 is a root that we're not able to simplify because it's a prime number. So the only factors of 17 are 1 times 17. And we could factor out 1, I suppose, but it's not going to make our answer any simpler because we would still just have 17 underneath the square root. In this next example, we're going to start by finding the square root of negative 2 squared plus negative 3 squared. And those negatives will become positive when we square them. 2 times 2 is 4. 3 times 3 is 9. We have the square root of 4 plus 9, which is 13, and we cannot simplify that square root any further. In this next example, we're going to do the square root of negative 6 squared plus 8 squared. That's the square root of 6 times 6 is 36, and 8 times 8 is 64. Square root of 36 plus 64 is the square root of 100, and we can take the square root of that perfect square, so we get square root. Square root of 100 gives us 10. All right, couple more examples here. We have the square root of 4 squared plus negative 8 squared. 4 squared, 4 times 4 is 16, and negative 8 squared is positive 64. So we have the square root of 16 plus 64, which is square root of 80. And 80 does have a lot of factors, so we should definitely check this and see if we could break this down any further. Some of the perfect square factors of 80 are, we could break it apart as square root of 4 times square root of 20. But there's actually an even bigger perfect square we could factor out, because if we still have a 20 underneath our square root, that still has factors of 4 and 5, and 4 is another perfect square inside of 20. So we really have 2 factors of 4 inside of that 80, which means the biggest perfect square factor we could factor out is we could actually write it as 16 times 5. And the square root of 16 is 4, so if we simplify this, we will get 4 times the square root of 5. I think we're going to need a little bit more space to work, so let me continue on the next screen here in just a second. All right, so to find the absolute value of negative 1 minus 7i, that is the square root of our real part squared, negative 1 squared, plus our imaginary part squared, which is negative 7 squared. Negative squared is still positive, so this is the square root of 1 plus 7 squared is 49. Square root of 50 And we can break apart 50 into a pair of perfect, 50 has a perfect square factor inside of it. We could write this as root 25 times root 2, where the square root of 25 is 5. So this is 5 times the square root of 2. You might notice that there's another way we could have factored 50. We could have tried like 5 times 10, but that doesn't help us if we're trying to simplify a square root because we want one of those factors to be a perfect square. And I'll just mention here that this formula still works even if we're trying to do a simpler calculation, like finding the absolute value of a real number on its own. We saw at the very beginning of this that the absolute value of 4 is, of course, just 4. But even if we consider 4 as a complex number with the imaginary part 0i, the same formula we use to calculate complex absolute value would still give us this answer. We could write this as the square root of 4 squared plus 0 squared. And that 0 squared will just cancel out. 0 squared is still 0. And the square root of 4 squared is, of course, just back to 4. So to find the absolute value of negative 1 minus 7i, that's the square root of negative 1 squared plus negative 7 squared. When we square those negative numbers, they will become positive. 1 times 1 is 1. 7 times 7 is 49. So we have the square root of 1 plus 49, which is 50. And we can simplify this if we break it down into a pair of factors. One of these factors is a perfect square. The root of 25 would give us 5. So this is 5 times the square root of 2. So finding the absolute value of a complex number is a little more complicated than what we did before to find absolute value of imaginary or real numbers, but it's all the same interpretation of what this absolute value symbol is measuring. In each case, it measures the distance that that number is from 0. And technically, this formula would still work if we were doing just the absolute value of a real number or an imaginary number on its own. It's just a little bit more work than we would need to do. But you could, if you wanted to, think of finding the absolute value of 4 as finding the absolute value of a complex number, 4 plus 0i. So what happens if we plug that into our formula where the imaginary part is 0? Well, that would be square root of 4 squared plus 0 squared. But of course, 0 squared cancels out. 0 times itself is still 0. So we just have the square root of 4 squared, which gets us 4, which is the same answer we would have had if we did it without applying the formula.